It is still out there, right now, at this exact second. A machine the size of a compact car, covered in gold foil, spinning slowly in the absolute dark, is moving away from you at 47,000 miles per hour. It has been doing this for 49 years. It has never stopped. It has never slowed down, and it is not going to. Voyager 1 is the farthest object humanity has ever built. Farther than any satellite, any probe, any fragment of metal or glass we have ever thrown into the dark. As of this moment, it sits more than 15 billion miles from the sun, so distant that the light leaving it right now will take over 22 hours to reach you. 22 hours. And light doesn't stop to rest. Light doesn't hesitate. Light simply travels at the maximum speed the universe permits. And even that is not fast enough to bridge the distance in a single day. Think about that. Really think about it. 15 billion miles is not a number your brain was built to understand. Evolution shaped your mind for savanna distances, for the gap between you and a lion, you and your tribe, you and the horizon. The cosmos operates on a scale so violently different that every attempt to grasp it collapses before it reaches full comprehension. But try anyway. If you drove a car without stopping, no gas, no sleep, no rest, at highway speed, 60 miles per hour, it would take you nearly 30,000 years to reach Voyager 1. The Roman Empire hadn't even risen yet when you would have had to leave. And yet, the machine is still alive. That is the part that should stop you cold. Not just that it traveled so far, but that it survived. That the instruments still function. That the radio antenna still knows which direction to point. That a signal still crosses that impossible gulf and arrives, faint, whisper thin, barely distinguishable from the background hiss of the universe itself, and is caught by enormous dishes on the surface of a small blue planet, decoded, interpreted, and understood. 49 years. No repair crew, no fuel stop, no reboot, no mercy from the void. Space is not empty in the poetic sense. It is empty in the most lethal, absolute, merciless sense the word can carry. Out where Voyager now drifts, in a region called interstellar space, beyond the protective bubble the sun throws around its family of worlds, the temperature of the background universe hovers just a few degrees above absolute zero. Not cold the way a winter night is cold, not cold the way the polar ice caps are cold. Cold in the way that means almost all molecular motion has ceased. Cold that would freeze your blood in milliseconds and shatter your bones like glass. Cold that makes the coldest place ever recorded on Earth feel like a roaring furnace by comparison. And Voyager has been inside that cold for decades. The radiation environment out there would destroy most electronics within years. High-energy particles from ancient supernovae, streaming through the galaxy for millions of years, pass through the spacecraft's structure with contemptuous ease, leaving trails of damage in their wake, flipping bits of data, degrading circuits, eroding the margins of every component. And yet, the machine transmits. And yet, the data arrives. It was launched on September 5th, 1977. The world was different then in ways that are difficult to fully catalog. Personal computers didn't exist in any meaningful consumer form. The internet was a small academic experiment connecting a handful of universities. The Soviet Union was alive and powerful. Most people alive on Earth today hadn't been born yet. The engineers who built Voyager used slide rules as backup calculation tools. The onboard computer, a machine that controls a spacecraft now in interstellar space, has less processing power than the watch on your wrist. Think about that ratio. The device tracking your steps, measuring your heartbeat, showing you the time in Tokyo. It is more powerful, in raw computational terms, than the machine that crossed the boundary of the solar system. That machine, the one no other object built by human hands has ever surpassed in distance, surpassed in audacity, surpassed in sheer, defiant longevity. How is this possible? That is not a rhetorical question. It is the question, the real question underneath the data and the mission reports and the press releases. How does a machine built in the 1970s, powered by a fuel source that decays a little more every year, operated by a computer with barely enough memory to hold a single low-resolution photograph, how does that machine survive 49 years in the most hostile environment in the known universe and still whisper back to us across 15 billion miles of absolute nothing? The answer is not simple. The answer touches engineering, physics, chemistry, thermodynamics, orbital mechanics, and something harder to name, a kind of institutional devotion, a multi-generational act of will that kept a signal alive long after everyone who first built the machine had aged and retired, and in many cases, left the world entirely. The answer will take time to tell properly. And that is what this is for. But before we move into the mechanics, before we talk about plutonium and radio transmitters and the specific genius of the engineers who designed a spacecraft to last longer than they could possibly predict, stop for one more second at the sheer weight of the image. 15 billion miles away, in a darkness your eyes were never built to see, in a cold your body was never meant to survive, moving at a speed no human being has ever experienced. A golden machine is turning slowly on its axis. Its antenna, a dish 11 feet across, is aimed with extraordinary precision at a dim yellow star, our star. So far away, it no longer looks like a star. From where Voyager sits, the sun is a bright point, a pixel, a slightly luminous needle in a field of needles. And the machine knows it. The machine finds it every day. It speaks to us from the dark, and we still hear it. That is what we are about to explain. Everything begins with heat, not the heat of combustion, not the crude chemical fire that burned the Saturn rockets and pushed the Apollo capsules skyward in a roar of controlled explosion. That kind of fire consumes itself. That kind of fire ends. What powers Voyager is something older, something more patient, something written into the architecture of matter itself. Radioactive decay, deep inside the spacecraft, sealed in containers engineered to survive virtually any catastrophe, including the catastrophic failure of the rocket that carried it. Sit pellets of plutonium-238. Not the plutonium of weapons and nightmares. A different isotope, far less fissionable, far more useful for a different purpose entirely. Plutonium-238 decays slowly, steadily, releasing heat as it sheds alpha particles, helium nuclei fired from unstable atomic cores at enormous velocity. That heat is captured, converted, turned into electricity by an arrangement of thermocouples, devices so simple in concept a 19th century physicist would recognize them instantly, that exploit the voltage generated when two dissimilar metals are held at different temperatures. No moving parts, no pistons, no turbines, no combustion chambers, just heat on one side, cold on the other, and the quiet, obedient flow of electrons between them. This is what a radioisotope thermoelectric generator does. The acronym is RTG. The concept is almost disarmingly modest for a device that has kept a machine alive for half a century in interstellar space. At launch, Voyager's 3 RTGs produced roughly 470 watts of electrical power, less than 5 standard light bulbs, less than a decent hairdryer, an amount of energy so small it feels almost insulting to the scale of the mission it was asked to sustain. And yet, it was enough, because space, for all its violence, offers one gift: the absence of resistance. There is no air to drag against the hull, no friction to convert momentum into heat. Once Voyager reached its cruising velocity, hurled outward by the gravitational slingshot of Jupiter and Saturn, it needed no additional propulsion. Physics carried it. Inertia, that most fundamental of all conserved quantities, became the engine. And inertia, unlike plutonium, does not decay. But plutonium does. This is the central tension of the mission, the slow arithmetic of survival. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half of whatever remains will have decayed into uranium-234, releasing no more heat, contributing no more electricity. The curve is exponential and inexorable. It does not negotiate. It does not pause. Since launch, the power output of Voyager's RTGs has declined by roughly 4 watts every year. A quiet hemorrhage, invisible and constant, draining the spacecraft's reserves the way a slow leak drains a tire. Imperceptibly at first, then faster, then suddenly critical. Right now, Voyager 1 operates on approximately 249 watts, nearly half of what it had at launch. Gone, converted, spent into the universe as uranium and heat and time. And those 249 watts must power everything. The computers, the instruments, the heaters that keep internal components from freezing solid in the interstellar cold, and most critically, the radio transmitter that bridges 15 billion miles of void to reach us. The response to this slow starvation has been a kind of triage that is almost philosophical in its nature. Over the decades, engineers have systematically turned off every system that could be turned off. Instruments that completed their primary science objectives were powered down. Heaters were disabled, one by one, allowing some components to cool to temperatures they were never designed to survive. And in some cases, surviving anyway, as if the hardware itself refused to acknowledge its design limits. Each shutdown bought time. Each watt saved was a watt that could keep the transmitter alive for another few months, another year, another orbit around the sun that Voyager itself would never complete. Think about what this means in human terms. It means that the engineers who manage Voyager today are not operating a spacecraft at full capacity. They are managing a patient on a diminishing life support budget, making careful, painful decisions about which functions to preserve and which to release. They are triaging a machine across interstellar space, issuing commands that take over 22 hours to arrive, then waiting another 22 hours for the confirmation that the command was received. 44 hours to know whether their decision worked. 44 hours of uncertainty, stretched over 15 billion miles for every single intervention. There is a word for that kind of patience. It is not a technical word. Now consider the transmitter itself, the radio signal that Voyager sends back to Earth. The thin thread that connects a golden machine in interstellar space to a species still confined mostly to a single planet, leaves the spacecraft at 23 watts. 23 watts. The bulb inside a refrigerator is typically more powerful than the signal that crosses 15 billion miles to reach us. By the time it arrives at Earth, after traveling for 22 hours at the speed of light, the signal has spread and diluted across an unimaginable volume of space. The power received by the largest antennas on Earth, dishes up to 70 meters across, is on the order of a tenth of a billionth of a watt. A number so small it has no meaningful analog in ordinary human experience. It is not the faintest whisper, and it is something below whisper. Below silence, it lives in the boundary zone where signal and noise become almost indistinguishable, where the mere act of amplification introduces its own distortions, where the receivers must be cooled to within a few degrees of absolute zero just to reduce their own thermal noise enough to hear what Voyager is saying. And we hear it. We hear it clearly enough to do science. This is what the RTG enabled. Not just survival, but communication. Not just presence in the void, but witness. Voyager didn't merely travel to interstellar space, it sent back measurements. It told us what the boundary of our solar system actually looks like from the inside, crossing it. It detected the shift in particle density as the solar wind gave way to the interstellar medium. It measured magnetic field orientations that confirmed theories about the heliopause, the great turbulent frontier where the sun's influence finally yields to the galaxy's background field. All of that science, all of that data, arriving on a signal thinner than a whisper, powered by a heat source built on the patient arithmetic of atomic decay. There is something almost unbearably elegant about it, if you let yourself feel it fully. The universe is built from processes that decay. Stars burn out, atoms break down. Entropy, the great tendency of all ordered systems to slide toward disorder, is the most fundamental force in thermodynamics, and by extension, in the long biography of the cosmos. Everything that exists is in the process of becoming something else, something less organized, something closer to equilibrium. And yet, humanity took one of those decay processes, the slow, inevitable disintegration of a plutonium nucleus, and harnessed it, redirected it, used the universe's own tendency toward disorder to power a machine that increases our understanding of the universe. Entropy turned against itself. Decay made to sustain. The void made to speak. That is what the RTG is at its deepest level. Not a battery, not an engine. A philosophical statement encoded in metal and isotopes. The declaration that intelligence can find the current in any river, even one flowing toward dissolution, and ride it outward into the dark. But power alone does not explain survival. There is another layer beneath the plutonium, beneath the thermocouples, beneath the careful triage of watts and instruments. A layer that has nothing to do with physics and everything to do with the specific, extraordinary minds that designed a machine to outlast their own certainty about the future. That layer is engineering, and it deserves its own accounting. There is a particular kind of hubris in building something you expect to fail, and there is a rarer, more difficult kind of wisdom in building something you dare to hope will not. The engineers who designed Voyager 1 in the early 1970s were not naive. They knew exactly where their machine was going, into a domain no instrument had ever entered, governed by conditions no laboratory on Earth could fully replicate. For a duration that exceeded any reasonable guarantee any manufacturer could offer on any component in existence. They could not test the spacecraft for 50 years before launching it. They could not simulate interstellar space in a vacuum chamber. They could not ask a supplier to warranty a transistor against 4 decades of cosmic ray bombardment and temperature extremes that would make most materials behave in ways their data sheets had never anticipated. So they did something else. They overbuilt everything. And then they backed up everything they had overbuilt. Redundancy is the foundational theology of spacecraft engineering, and Voyager was its cathedral. Critical systems were duplicated, in some cases triplicated, computers, attitude control thrusters, receiver systems, data recorders. If one failed, another waited in cold reserve, untouched, preserved, ready to be activated by a command from Earth or by the spacecraft's own autonomous fault protection logic. The philosophy was not optimism. It was the systematic acknowledgement that failure, in some form, was inevitable, and that the only response to inevitable failure is to ensure that no single failure is permitted to be final. This is a profound engineering principle. It is also, if you step back far enough, a profound life principle. The systems that endure, biological, social, technological, are rarely the ones that never break. They are the ones built with enough internal redundancy that breakage in one place does not cascade into total collapse. Resilience is not the absence of failure. Resilience is the architecture that contains it. Voyager's computer system is a case study in that architecture. The spacecraft carries 3 interconnected computers. A command computer subsystem that receives and executes instructions from Earth. A flight data system that formats data for transmission. And an attitude and articulation control system that keeps the spacecraft oriented correctly in space. Each of these runs on hardware that, by modern standards, is almost incomprehensibly limited. The total memory across all 3 systems is measured in kilobytes, not megabytes, not gigabytes, kilobytes, the amount of data contained in a few paragraphs of plain text. And yet these machines have been running without interruption for 49 years. No reboot, no operating system update, no patch, no fix, no replacement of corrupted files. The same code, written by human hands in the 1970s, executing the same instructions in the same sequence, billions of times over. In the dark between the stars, there is something almost monastic about it. A kind of digital vow of continuity. An unbroken thread of computation stretching back to a decade when the world looked almost nothing like it does today. But the hardware was not invulnerable. It was never meant to be invulnerable. It was meant to fail gracefully. And it has, multiple times, in ways that revealed just how carefully its designers had thought about the nature of long-duration failure. In 2022, something went wrong with Voyager 1's flight data system. The telemetry it was sending back to Earth became garbled, not absent, not silent, but scrambled in a way that suggested a corruption somewhere in the readout process. Scientists and engineers at the Jet Propulsion Laboratory faced a problem of almost surreal difficulty. Diagnosing a malfunction in a computer the size of a shoebox. Running 49-year-old code located 15 billion miles away. With a round-trip communication delay of 44 hours per exchange. Imagine debugging a machine you cannot touch, cannot see, cannot power cycle, where every question you ask takes 2 days to receive an answer. Where the documentation for the system you are trying to repair was written before some of your team members were born. Where the engineers who originally designed the faulty component are mostly gone, and what remains of their knowledge lives in archived paper documents, scanned and digitized, searched with the desperation of archaeologists hunting for a key that might no longer fit the lock. It took months. It took the kind of patient, methodical, almost archaeological detective work that has no glamour in it. Only the slow accumulation of understanding, clue by clue, inference by inference, hypothesis formed and tested across the void at the speed of light. And they fixed it. In April 2024, engineers identified that a single corrupted chip in the flight data system had caused a small portion of the spacecraft's memory to malfunction. producing the garbled telemetry. Their solution was elegant in the way only deeply constrained engineering solutions can be elegant. They reformatted the software, redistributing the affected code across other, undamaged sections of memory, working around the broken chip entirely. The fix was uploaded. The signal crossed 15 billion miles. The spacecraft received it, executed it, and began sending back clean data again. Clean data from interstellar space, from a machine built in the Nixon administration. There is no precedent for this. There is no manual that covers the repair of a 49-year-old spacecraft in interstellar space, because no such spacecraft has ever existed before. Every problem Voyager develops from this point forward will be, by definition, a problem no one has ever solved before. A problem at the outer edge of human experience, in the most literal sense of that phrase. The people solving these problems are not just engineers. They are pioneers in a domain that has only one occupant. But the engineering marvel is not only in the redundancy, it is also in the precision. Consider the antenna. Voyager's high-gain dish, the primary instrument of communication, the ear and mouth of the spacecraft, must remain pointed at Earth with extraordinary accuracy. Not approximately, not roughly. The pointing error must be less than a fraction of a degree, maintained continuously across billions of miles, for decades, using thrusters that burn hydrazine fuel in pulses measured in milliseconds. If the antenna drifts even slightly off axis, the signal weakens. If it drifts far enough, the signal dies entirely, and the spacecraft becomes a mute object, present but unreachable, alive but silent. The attitude control system that prevents this uses gyroscopes and star trackers, instruments that find their position in space by identifying known star patterns and comparing them against an onboard reference catalog. The stars, from Voyager's vantage, look slightly different than they do from Earth, shifted by the spacecraft's extraordinary remove from the solar system's center. But the geometry holds. The mathematics is exact. And so the machine knows where it is, knows which way it is pointing, and knows how to correct itself when it drifts. It navigates by starlight, the way sailors once did, crossing dark water on wooden ships, trusting the fixed architecture of the sky to tell them where they stood in relation to the world. Voyager does this not with a sextant and a trained human eye, but with silicon and code and the patient recursion of a computer that has never once forgotten what it was built to do. And perhaps that is the deepest thing about the engineering. Not the redundancy, not the precision, not the remarkable fact of software written 50 years ago, still executing correctly in the coldest, darkest, most remote location any human artifact has ever occupied. The deepest thing is the intention embedded in the design. The engineers who built Voyager made choices, thousands of choices, that would only pay off decades after they made them, in conditions they could model but never fully predict, for a mission duration that exceeded any reasonable professional expectation. They built not for the moment of launch, not even for the planetary encounters that justified the mission. They built for the long silence afterward, for the decades of drift through the outer dark, for the possibility, not the certainty, but the possibility, that the machine might still be worth listening to long after the primary mission had concluded. They built for a future they would not live to see fully. That is not engineering. That is a form of faith. And faith, it turns out, is load-bearing. There is a boundary out there. You cannot see it. You cannot stand at its edge and look across it. It has no color, no texture, no physical surface to press your hand against. And yet, it is one of the most consequential borders in the known universe. A frontier so significant that crossing it changed the nature of everything Voyager was measuring, transformed the data streaming back from the spacecraft in ways that confirmed a theory physicists had carried for decades without proof. It is called the heliopause, and Voyager 1 crossed it on August 25, 2012. To understand what that means, truly understand it, not just register it as a date on a mission timeline, you have to understand what the heliopause actually is. The sun is not a passive object. It is a furnace in constant violent eruption, hurling a continuous stream of charged particles outward in every direction at speeds between 250 and 750 kilometers per second. This stream is called the solar wind, and it does not stop at the orbit of Pluto. It does not stop at the edge of the Kuiper Belt. It presses outward, relentlessly, in every direction, carving a vast bubble of solar influence into the surrounding interstellar medium. The thin, cold, ancient gas and dust that drifts between star systems across the galaxy. That bubble is called the heliosphere. Everything inside it, every planet, every moon, every comet and asteroid and grain of dust that orbits our sun, exists within the sun's sphere of influence, sheltered to some degree by its magnetic field and particle output. Earth sits near the center of this bubble, protected not only by its own magnetic field, but by the vast outer architecture of the heliosphere itself, which deflects and slows a significant fraction of the galactic cosmic rays that would otherwise reach us with full, unmediated force. We have always lived inside this bubble. Every human being who has ever existed, every civilization that has ever risen and fallen, every thought ever conceived, every word ever written, all of it occurred inside the heliosphere, inside the sun's embrace, inside the boundary the sun draws around itself against the rest of the galaxy. Voyager 1 left that embrace. The moment of crossing was not a single clean event. The heliopause is not a wall. It is a turbulent, dynamic zone where the solar wind's pressure finally equilibrates against the pressure of the interstellar medium, a region of magnetic complexity and particle chaos that took years of data analysis to fully characterize. But the signature was unmistakable. The density of particles around Voyager changed abruptly. The magnetic field orientation shifted. The population of low-energy solar particles, the fingerprints of the sun's wind, dropped sharply, replaced by a flood of galactic cosmic rays that had previously been partially excluded by the heliosphere's outer layers. Different particles, different field, different space. Voyager had not just traveled far, it had traveled into a qualitatively different environment, one that no instrument had ever directly sampled before. The interstellar medium, that ancient diffuse ocean between the stars, had been studied from the inside of the heliosphere through inference and indirect measurement for decades. Now, for the first time, a human instrument was inside it, tasting it directly, reporting back with measurements that confirmed the theoretical models in some ways and complicated them in others. The magnetic field at the heliopause, for instance, turned out to be more aligned with the heliospheric field than many models had predicted, suggesting a smoother, more organized transition than the turbulent picture some theories had drawn. The density of electrons in the interstellar medium was measured directly for the first time, using plasma waves excited by solar events whose effects propagated all the way to Voyager's position. These measurements had implications not just for our understanding of the local interstellar environment, but for models of how stellar systems interact with the galaxy around them. models that apply not only to our sun, but to every star harboring planets anywhere in the Milky Way. Consider that implication. By crossing a boundary 15 billion miles from Earth. A 45-kilogram instrument package gave humanity its first empirical data about the environment in which all planetary systems exist. It made the local interstellar medium a measured reality rather than a theoretical construct. It turned a region of the universe that had existed only in equations and inference into something known, directly, irreversibly known, through the act of physical presence. This is what exploration does at its most fundamental level. Not merely extend the map, but transform the nature of knowledge itself, converting the hypothetical into the witnessed, the modeled into the measured, the imagined into the real. And Voyager keeps moving through it. Right now, the spacecraft is not stationary in the interstellar medium. It is traveling through it at roughly 17 kilometers per second, about 38,000 miles per hour, drifting away from the heliosphere in the direction of the constellation Ophiuchus, toward a region of the sky near the boundary of Ophiuchus and Hercules. It will not reach the next nearest star system, the Alpha Centauri complex, roughly 4.2 light-years away, for approximately 73,000 years. And it is not even heading in that direction. The stars are simply too far apart, and space between them too vast, for a journey between stellar systems to be anything other than an almost incomprehensible act of patience. 73,000 years. Humanity invented agriculture roughly 10,000 years ago. Written language is perhaps 5,000 years old. The entire span of recorded human history, every empire, every war, every philosophical revolution, every scientific breakthrough from Archimedes to Einstein, fits inside 12,000 years. Voyager will need 6 times that span just to reach the gravitational neighborhood of the nearest star. And it will arrive there, in all likelihood, as a silent object. Dead. Cold. Its plutonium long exhausted, its computers long dark, its antenna no longer pointing anywhere with purpose. A piece of human metal drifting through a stellar system it was never aimed at. Carrying instruments that no longer function and a golden record that still holds its contents perfectly. Sealed in the vacuum that has preserved it for tens of thousands of years, without oxidation, without decay, without any of the entropic forces that destroy things on planetary surfaces. The golden record, it deserves its own moment here, because the record is perhaps the most philosophically audacious object human beings have ever manufactured. It is a 12-inch gold-plated copper disc affixed to the side of the spacecraft, containing sounds and images selected to represent the diversity of life and culture on Earth. Music from dozens of traditions, greetings in 55 languages, the sound of wind, rain, surf, thunder, the sound of a mother's first words to a newborn child, mathematical diagrams, anatomical illustrations, instructions encoded in pulsar timing and physical constants for how to build a device capable of playing it. It was built for an audience that may not exist, sent into space with the full awareness that the probability of another intelligence finding it in the vastness of interstellar space over any timescale a human mind can grasp is vanishingly small. And yet, it was made anyway, curated with genuine care, with arguments about which music to include and which images best represented the breadth of human experience. Sent outward not as a rational bet on contact, but as something more fundamental, a gesture, an act of reaching toward the unknown with open hands. If no one ever finds it, it still mattered that it was made. because the making of it says something about the species that made it. That at the height of the Cold War, with two nuclear superpowers staring at each other across an ideological abyss, human beings chose to put the sound of a mother speaking to her child onto a golden disc and throw it toward the stars. Not as propaganda, not as power, as an introduction. The frontier Voyager crossed in 2012 was physical. The frontier the golden record represents is something else entirely. The boundary between a species turned inward toward its own conflicts and horizons, and a species that has begun, however tentatively, to look outward, to acknowledge that the universe is larger than its wars, older than its gods, more patient than its civilizations, and worth speaking to. On February 14, 1990, someone asked Voyager 1 to turn around, not permanently, not to come home, just to turn its camera. A camera that had already been largely powered down after completing its planetary mission, back toward the inner solar system one final time, before the instrument was shut off forever to conserve power. The person who asked was an astronomer, a writer, a man who had spent his career trying to communicate the scale of the cosmos to people who had never been forced to reckon with it. His name was Carl Sagan, and the image that resulted from his request became one of the most consequential photographs ever taken. It is called the Pale Blue Dot. From a distance of approximately 3.7 billion miles, Voyager's camera captured the inner solar system in a series of images later assembled into a mosaic. And there, in one frame, suspended in a beam of scattered sunlight that crossed the camera's field of view at precisely the wrong, or perhaps precisely the right, angle, was Earth. Not a globe, not a world. A point, a pixel, a mote of dust suspended in a sunbeam, to use the words Sagan himself wrote when he saw it. That was us. That has always been us, from any sufficient distance. The image does something to the mind that no argument, no lecture, no philosophical treatise quite manages. It does not tell you that Earth is small. It shows you. And there is an unbridgeable difference between being told a thing and being confronted with its evidence. The photograph is not a metaphor. It is not an artist's impression. It is a literal geometric fact, a measurement of angular size, of photons reflected off oceans and continents and clouds, captured by a camera pointed backward across billions of miles. The smallness is not a feeling. It is a datum. And yet, everything you have ever loved exists in that pixel. Every person who has ever lived was born there. Every war ever fought was fought on that dot. Battles over borders that, from Voyager's vantage, are not merely invisible but cosmically irrelevant. Scratches on a grain of sand at the bottom of an ocean. Every monument ever built, every library ever assembled, every song ever sung into the dark, compressed into a point of light so small that the camera very nearly missed it. Sagan understood what the image meant before he saw it, because he understood the geometry. But understanding something mathematically and experiencing its visual proof are not the same cognitive event. Even he was struck. Even he, who had spent decades thinking about exactly this kind of scale, found himself confronted with something that exceeded his prior engagement with the concept. That gap between knowing and seeing is where Voyager has always lived. Because Voyager is not merely a scientific instrument. It is a perceptual device. It does not only measure the interstellar medium and report on magnetic fields and particle densities. It generates vantage points that no human being has ever occupied. Positions in space from which familiar things become unfamiliar. from which the architecture of the solar system becomes visible as an architecture rather than a set of individual facts, from which the sun shrinks to a bright point and the planets disappear entirely, and the sheer, annihilating scale of even the local neighborhood of one ordinary star in one ordinary galaxy becomes something you can almost feel. Almost. Because the other thing the pale blue dot revealed, quietly, without fanfare, embedded in the geometry of the image itself, is the limit of human perception across cosmic distance. The photograph was taken at 3.7 billion miles. Voyager is now more than 4 times farther away. Its cameras have been off for decades. There will be no more photographs, no more backward glances. The machine continues its journey in a kind of enforced blindness. Instruments pointed outward into the interstellar medium, measuring what surrounds it, but no longer able to look back at where it came from. We are the ones who look back now. We look back at the image, at the mission, at the 49 years of continuous operation and everything they represent about what a species, in its early technological adolescence, managed to accomplish with slide rules and kilobytes, and a genuine, burning desire to know what was out there beyond the last planet. And what Voyager found, what the totality of its journey has revealed, layer by layer, from Jupiter's moons to Saturn's rings, to the heliopause, to the interstellar medium, is not reassurance. It is not the comforting discovery that the universe is comprehensible at human scales, that its distances are manageable, that its timescales align with anything a biological mind can intuitively grasp. What Voyager found is the opposite. It found a cosmos of almost incomprehensible indifference to scale, a universe in which the distance between 2 neighboring stars is so large that a spacecraft traveling at 38,000 miles per hour requires 73,000 years to cross it, and in which that crossing represents a journey between 2 points that are themselves lost in a galaxy of 400 billion stars, in a universe of 2 trillion galaxies. That is not a comforting number. That is not even really a number, in any experiential sense. It is a symbol standing in for something the human nervous system was not designed to metabolize. We write it. We say it. We nod as if we have understood it. And then we go about our lives at human scales, in human time, because there is no other way to go about them. But Voyager will not go about its journey at human scale. In roughly 5 years, perhaps a decade at most, the power budget will drop below the threshold required to operate any scientific instrument at all. The heaters will be gone. The computers will lose their ability to process and transmit data. The signal will weaken below the threshold of detectability even by the largest antennas on Earth. And Voyager 1 will become, for all practical purposes, silent, present, still moving, still carrying its golden record through the interstellar dark, but no longer speaking. The silence, when it comes, will not be a failure. It will be the natural conclusion of a conversation that lasted longer than anyone dared predict when it began. A conversation between a civilization and its first true emissary to the galaxy. 50 years of data, of discovery, of position reports from the outer dark, of measurements that rewrote textbooks and answered questions that had been open since before the space age existed. And after the silence, the motion will continue. This is the part that carries the most weight, if you let it. Long after the last signal fades, long after every person now alive on Earth is gone, long after the civilizations that currently exist have transformed into whatever comes next, or ended entirely as most civilizations have, Voyager 1 will still be moving, still carrying its cargo of human intention through the interstellar medium, not decelerating, not drifting into a decaying orbit, moving in a straight line at constant velocity, exactly as Newton's first law demands. Because in interstellar space, there is nothing significant enough to stop it. In 40,000 years, it will pass within 1.6 light-years of a dim red dwarf star called Gliese 445, located in the constellation Camelopardalis, not close enough to be captured by its gravity, not close enough to illuminate the spacecraft or warm it, just close enough to be the nearest star to Voyager at that moment in cosmic time. A proximity measured in light years, which is to say, a proximity that would take human technology as it currently stands tens of thousands of additional years to traverse. And still it will not stop. It will pass Gliese 445 and continue outward into regions of the galaxy no theoretical model has yet fully mapped, carrying a record of a species that existed briefly on a pale blue dot, that learned to split the atom and write symphonies and feel grief and wonder and love. And that chose, in one of its finer moments, to throw a golden disk into the dark as proof that it had been here, that it had looked up, that it had tried to reach. The machine will outlast the memory of everyone who built it. It will outlast the institutions that funded it. It may outlast the civilization that conceived it. And it will carry, in its silent golden cargo, the sound of a world that once existed and chose, against all rational probability, to introduce itself to the universe. That is what Voyager is. Not a spacecraft. A message in a bottle thrown into the largest ocean there is. Ask yourself a question. Not a comfortable one. Not the kind of question that resolves itself neatly into an answer and lets you move on. Ask yourself the kind of question that stays open, that sits in the chest like a stone and refuses to dissolve even after you have thought about it carefully. Even after you have accumulated all the relevant facts and arranged them in order and done everything a rational mind is supposed to do with difficult material. The question is this: what does it mean that we built something that outlasted our certainty? The engineers who designed Voyager 1 did not know it would still be operating in 2026. They could not have known. The mission's primary objectives were the planetary encounters, Jupiter, Saturn, the moons, the rings. Those encounters concluded by 1980. Everything that came after was bonus, overflow, grace. The spacecraft kept functioning not because anyone guaranteed it would, but because the people who built it made decisions, thousands of them, that collectively added up to a machine capable of surviving conditions no one could fully predict, for a duration no one could fully promise, in a domain no instrument had ever entered. They built better than they knew. That phrase deserves to be held for a moment, because it contains something important about the nature of great human work. The best things we make consistently exceed the understanding of the people who made them. The builders of the great cathedrals of medieval Europe did not fully understand the structural mathematics of the Gothic arch. They worked by intuition, by accumulated craft knowledge, by trial and error across generations. And yet the cathedrals stand 800 years later, their stone still holding, their geometry still sound, their presence still capable of producing in a visitor something that exceeds what any purely rational account of cut stone and mortar should be able to produce. Voyager is the cathedral of the space age, not because it is beautiful, though in its way it is. The gold foil gleaming against the black, The dish aimed with such precision at a star, it can no longer see as anything but a point of light. But because it stands, because it endures, because something built by human hands in a specific historical moment, shaped by the constraints and capabilities of that moment, turned out to contain more than its makers consciously put into it. More resilience, more longevity, more meaning. And now consider what Voyager's survival asks of us. We live in an era defined, more than almost any other quality, by the speed of obsolescence. The device in your pocket will be replaced within 2 years. The software running on it will be deprecated within 5. The platforms that structure your social life will be unrecognizable within a decade. The pace at which we build things and discard them, the metabolic rate of our technological civilization, has accelerated to a point where the very concept of something lasting feels almost quaint, almost naive, the kind of sentimental attachment that pragmatic people are supposed to have grown out of. And into this culture of disposability, Voyager sends back its signal. Every day, a machine built with slide rules and kilobyte computers, launched before the personal computer existed, still transmitting across 15 billion miles, still doing science, still speaking quietly, faintly, but unmistakably, across the largest distance any human artifact has ever spanned. It is not a rebuke exactly. Voyager does not judge. It simply persists. But its persistence functions as a kind of mirror, held up to everything we have built since. All the faster, cheaper, more sophisticated, more connected, more powerful technologies that have come after it, almost none of which will still be operating in 50 years, let alone transmitting data from interstellar space. The mirror asks a question the reflection has to answer for itself. What are we building for? Because Voyager was built for something larger than its immediate utility, larger than its budget justification, larger than the careers of the people who designed it, or the political moment that funded it, or the specific scientific questions it was tasked with answering. It was built with a kind of implicit awareness that the universe is older than any human project, and that anything worth doing in the presence of that oldness ought to aspire to a duration commensurate with the ambition of the undertaking. That is a rare ambition. It is rare in individuals and rarer still in institutions, which tend naturally toward shorter time horizons, toward the quarterly report, the election cycle, the funding renewal, the next product launch. The systems that govern human activity are almost uniformly optimized for the near term. And yet Voyager, funded by a government, designed by an institution, built by engineers with mortgages and deadlines and performance reviews, somehow escaped that gravity, somehow produced something that operates on cosmic timescales rather than fiscal ones. How? Partly through the particular genius of the individuals involved, partly through a set of cultural conditions at NASA in the 1960s and 70s that permitted a kind of patient, meticulous, long-horizon thinking that is difficult to sustain in any organization over time. Partly through luck, the right people in the right place at the right moment in history, before the full weight of bureaucratic risk aversion settled onto the institution and changed what it was capable of producing. And partly, this is the part that is hardest to name, through love. Not a sentimental love, not the love of popular song and greeting cards, the love of complete absorption in a problem, the love that makes a person spend their working years thinking about how to keep a signal alive across distances that dwarf the imagination, how to protect a machine from conditions that exceed any laboratory's ability to replicate, how to write software that will still execute correctly when the computers that run it are 50 years old and the people who wrote the code are gone. The love that is indistinguishable from the outside, from obsession, and that produces, when it finds the right object, work that outlasts the lover. The people who built Voyager are mostly gone now, retired, aged, many of them dead. The machine they made is farther from Earth than anything they could touch or see or directly influence. Farther than their hands can reach by a margin that makes the word reach feel almost comically inadequate. And yet, the machine carries their decisions forward, executing their choices every millisecond in the dark between the stars. There is a word for that too. It is legacy, but not in the diluted sense the word has acquired in the language of professional ambition and personal branding. Legacy in its oldest, most precise meaning, something left behind that continues to act in the world after the one who left it is no longer present to direct it. A force that persists, a cause that keeps producing effects long after the initial impulse has faded. Voyager is the longest legacy in human history. Not the most famous, not the most powerful, not the most culturally transformative, but the longest, the one that will still be moving, still carrying its cargo of human intention after every other artifact of this civilization has been buried, corroded, burned, forgotten, or transformed into something unrecognizable. The pyramids will erode. The great libraries will burn again, as they always have. The digital records will corrupt, their formats obsolete, their storage media degraded. The golden record, sealed in vacuum, will still hold its contents intact, and Voyager will still be moving. In the end, what Voyager 1 reveals about humanity is not our power. Our power, measured against the scale of the cosmos, is negligible. A species on a pale blue dot, briefly energetic, throwing small metal objects into a void so vast that those objects will travel for geological timescales without encountering anything significant. We are not powerful in any cosmic sense. We are not central. We are not necessary to the operation of the universe, which ran for 13.8 billion years before we arrived, and will continue running for an almost incomprehensible duration after we are gone. What Voyager reveals is our reach. Not our physical reach, which is real but modest. Our imaginative reach, the capacity of this species, fragile, brief, often foolish, frequently cruel, but occasionally and genuinely magnificent. To conceive of something beyond its own horizon, and then build it. To ask what is out there and then go, not in body, but in proxy. To send a piece of itself into the dark as an act of genuine curiosity, genuine wonder, genuine desire to know. 49 years, 15 billion miles, still transmitting. The universe did not ask us to listen. It did not arrange itself to be comprehensible, or to reward our attention, or to offer us comfort in proportion to our effort. It simply is. Vast, cold, ancient, indifferent, and astonishing beyond any capacity we have to fully absorb it. And we listened anyway. We built a machine and threw it into the dark and kept our ears pointed at the sky for half a century, waiting for the whisper to come back. It still does. Every single day. That is not nothing. That is everything.